Thanks for joining me in today's lesson. In this tutorial, we will state and use the properties of logarithms, and we will use them to expand and condense logarithms. So we're in section 4.5 in our textbook, and we're looking at all 8 of our properties today. Now we've already looked at 5 of the basic log properties in a previous tutorial, so let's do a quick recall of those. The log base A of 1 is equal to 0. The 0 power creates the 1. The log base A of A is 1 because A has to be raised to the first to be itself. The log base A of base A to the x equals x, so the log base A and the exponential A base cancel away, and reverse the exponential base A to the log base A of m, those cancel away so that we're left with m. And then our equality of logs property, log base A of x equals log base A of y if and only if x and y are equal. So those are our 5 basic ones, and we've already seen those. What we're going to look at and use today are 3 more. The log of a product, the log of a quotient, and the log of something raised to a power where the base is not the same. Don't get this third one confused with this one, the log base A of A. We're dealing with the same bases here. Here, in this third one here, we have different bases. Okay, so I like to think of my laws of exponents when I'm trying to remember these logarithmic properties. When we have the log of a product, I like to think about when we had back in Algebra 1 the product of two of the same bases, something like x cubed times x squared. And I remember that we add the exponents, of course. So since we're multiplying the same bases, we add the exponents. I'd like to think of that over here. When we're multiplying numbers in a logarithm, I can split the logarithms up and write the log base A of m plus the log base A of n. I can split this log of a product into 2 separate logarithms with one factor in each, and that's a plus sign. I'm adding up 2 exponents ultimately, and I know that I add the exponents when I was multiplying the same bases. So that's how I remember that one. When we have the log of a quotient, I like to think back here to something like x cubed divided by x squared. When we had the quotient back in Algebra 1, we subtracted the exponents. So it would make sense here when we're dealing with logarithms that the log base A of m take away the log base A of n would be true. So when you have the log of a quotient, you can expand that into 2 separate logarithms with a subtraction in between them. Make sure that the order matters. It's the numerator that comes first, m, subtracting the log of the denominator. The order, of course, matters. And in our final log property, we have the log base A of m to the p. So I like to think of that when we have something like x cubed and we raise it to yet another power. That's the instance where we multiply our exponents. 3 times 2. So when we have this, ultimately what we can do with this exponent that's m raised to the p power, we can bring that exponent out here and multiply it times the log base A of m. So it's sort of like this exponent of p multiplied to this exponent of log base A of m. So it's still 2 exponents multiplied together. So again, I like to think of the Algebra 1 laws of exponents to help me remember these logarithmic properties. Now these are equal signs. These properties, of course, involve equal signs, so we can have the log of a product and split it up, or we could have 2 logs being added together. As long as they're the same bases, we can condense them back into a single logarithm. When we use the properties this way, we are expanding. When we use the properties this way, we are condensing. Those are going to be the 2 verbs that I use, expanding and condensing. So when we use these properties this way, we are expanding, and when we use them backwards, we are condensing. So let's use this idea and play a little game here in example 1. What I'd like to do is take the natural log of 6 and rewrite it using only natural logs of 2 and or natural logs of 3. So what I want to do here is the natural log of 6, I can think of the natural log of 6 as the natural log of 2 times 3. I believe that that would definitely help me. I basically now have a log of a product. And a log of a product, according to my first property on the previous sheet, says that I can split this up into 2 logs, excuse me, not logs, natural logs. Yep. Ln of 2 plus the ln of 3. So I can expand the log of this product into the sum of the 2 individual logs together. So that works. My second one, I want to rewrite the natural log of 2 27ths using only natural logs of 2 and natural logs of 3. So the first thing I might say is, you know what, I've got the natural log of a quotient. I'm going to split that up into the natural log of the numerator, take away the natural log of the denominator. That might be my first move, and that's good. This part works according to our rules, but the natural log of 27 now needs to change. I can only use 2's and 3's, and 27 is not just some random number. I know that the 27 is 3 cubed. So I might write this as the natural log of 3 cubed, because then I can use my power property and bring this 3 on outside and write this as the natural log of 2 minus 3 natural log of 3. And that'll do it. There's another option, of course. Some people might say that the natural log of 27 instead is the natural log of 3 times 3 times 3. And that, of course, is correct. And then you could split that up into the natural log of 3 plus the natural log of 3 plus the natural log of 3 again. But guess what? You have 3 like terms that add to become 3 natural logs of 3. I don't really like that line. I'm going to erase that. I don't want you to think that there's a division. So you could do it by that method as well and use the product property and have 3 logarithms added up. But please understand that these, of course, are common like terms. So I can add them up and make 3 of them. So this would be our final answer. Okay, now let's change gears and let's expand we have different variables and different numbers, but the direction here is expand fully. We want to express any powers as factors, meaning that we should not see any exponents in our final answer. So I've got the log of 5x cubed y. So this is a product of 3 things. Now I want you to understand that I see that there's an exponent here, this cube, but I cannot just pull this exponent out first. This exponent of 3 does not refer to any other parts other than the x. So I would have to separate this x cubed before I can take out this 3. So I can't do that. The first thing is the product property. I have to split this up. In fact, I'm going to split it up into 3 separate logarithms and write it as the log of 5 plus the log of x cubed plus the log of y. So 3 separate logarithms using our product property. The log of 5, well, I don't know what that's equal to, so I'll leave it as that. The log of x cubed, now I can pull this 3 directly out front of this logarithm. And the log of y, well, the log of y is just log of y, so it looks like I'm finished. The log of 5 stays. I'm going to write this as the 3 log of x, and I'm going to write this as the log of y, which does not change. So that is expanding fully. This is what I mean by the parentheses here. Exponents express the powers as factors. 3 is now a factor because it's being multiplied to the log of x. Let's look at B. A little bit trickier, a lot of things going on here. The first thing I might want to do, actually the first thing I might want to do is move it over a little bit. The first thing I'm going to use my quotient property because I have a big fraction, so I'm going to do that. I'm going to write the log base 5 of my numerator, take away the log base 5 of my denominator, 25x minus 1 cubed. That's going to be my first thing. If you try to do too many things at once, most likely you'll mess up a little bit along the way. So I suggest going one step at a time. So now I see that I can bring this exponent of the 2 right outside, so I can write this as 2 log base 5 of x. I've got that. Now I have a product again, but beware. I have a subtraction in front of this log of a product. So if I'm going to split this log of a product, which I'm going to, if I split it up into 2 separate logs, understand that I'm subtracting both of them. So maybe I like to do it in parentheses, log base 5 of the 25 plus log base 5 of the x minus 1 cubed. And let me put this other parenthesis here. Okay, I'm splitting this product into 2 separate logarithms with a plus sign, but I'm about to subtract both of those logarithms, so it's like a distribution. Now, watch out for that sign. So I've got 2 log base 5 of x minus the log base 5 of 25 minus again the log base 5 of x minus 1 cubed. Okay, looking good. We've got 2 more things we can do. Clearly we have this exponent of a 3, and I'm going to bring that right outside here. But there's something going on with this. When I wrote that down, or at least when I said that, something rang a bell in my head. Log base 5 of 25. Do you know what log base 5 of 25 is equal to? Sure, I do. That's something that can simplify. The log base 5 of 25 is 2. So this is going to simplify to become a 2. You don't want to leave log base 5 of 25 in your work. That's sort of like leaving, 5/10 as your final answer. We all know that 5/10 would reduce to 1/2. So don't do something like that. Leave this or simplify this to a 2. Okay. If this were log base 5 of, I don't know, 20, then I would probably just leave it. Sort of like I did the log base 10 of 5 here. Didn't do anything more with that because I don't know what that's equal to. But this one clearly is a 2. And now I'm going to bring this 3 outside here, and I'll be left with 3 log base 5 of the x minus 1 needs to stay in parentheses. And I have my final answer. I expanded fully. A lot of steps on that one. So that's our expanding, taking one single logarithm and expanding as far as we can into multiple logarithms. Let's go backwards and condense. This time our verb is condense. So we're basically using our properties backwards. It says condense into a single logarithm. So in our final answer, we should have one logarithmic symbol. And let's see how we can do with that. Basically, you're doing what we just did, but backwards. The last step that we did in most of those was pulling exponents out. So that must mean in condensing, we're going to bring them back in. This 1/2 is going to come in. This 5 is going to come in. This 3, oh, that's confusing. I wonder what this 3 is going to do. Oh well, we'll deal with that when we need to deal with that. Let's bring in the 1/2. Okay, so we have the log base, well, it must be base 10. I don't see anything, so I'll just say the common log of x to the 1/2 plus the common log of x plus 1 to the 5th power plus, I don't know, 3. That's weird. It's not even a logarithm. Again, we'll deal with that when we need to. Okay, so this is 1/2 power. That's a square root. I'm going to change that to a square root. And what I might want to do now is condense these 2 logarithms together into a single logarithm. And now this plus sign means that I'm going to be able to do that by multiplying the 2 factors here. So x to the 1/2, but I am going to change that to the square root of x. And the x plus 1 to the 5th power, I'm just going to leave as x plus 1 to the 5th power. But we still have this 3 out there. Now what are we going to do with this 3? Because I'm not able to condense these 2 things together because there's no logarithm symbol over here. Maybe I need to convert this into a logarithm. So if I have the log of the square root of x times x plus 1 to the 5th power, and I need this to be the log of something, well, I do need to know that I'm dealing with base 10, and this is an exponent. So 3 is going to be the log base 10 of what? Meaning, what does 10 have to be, 10 raised to the third power is what? Ah, now I know it, it's 1,000. So this 3 must have been like over here where we had this 2. We wouldn't be able to deal with this 2 unless it had a logarithmic symbol, so we'd have to change it into the log base 5 of 25. And I know that I needed to use the base 5 because all the other symbols were log base 5s. I know that 2 has many names. Log base 5 of 25 is one of them. In this case, this 3 needed to convert into logarithmic form, but it needed to be base 10, so that's why I needed 1,000 right here. And now I can do the last step, which is to condense one more time with this plus sign into a single logarithm, and I'm going to put the 1,000 first. 1,000, then the square root of x, then the x plus 1 to the 5th power. Condensed all into one single logarithm. That's a good problem. So our final little section here is the change of base formula. This is a way of plugging anything into our calculator. Right now we have two buttons, the common log button and the natural log button. And obviously those are very limited because we can only use base 10s and base e's. So what if we had something like a base 5? So the log base anything of anything there's a change of base formula, and I'm going to prove this formula to you in a later tutorial when we start solving some equations. The log base a of x can be rewritten as the common log of the number divided by the common log of the base. You can use common logarithms. It's also equal to the natural log of the number divided by the natural log of the base. It doesn't really matter if you use common logs or natural logs. Now remember which goes into the numerator, and how I always remember is it's the number that is ultimately higher. The x is a little bit higher than this subscript. The log of x divided by the log of a. That's what the change of base formula says we can do. So that means that if we wanted to evaluate anything, we can do that in the calculator. The log base 5 of 89 is equal to the log of 89 divided by the log of 5. Now we can plug that into the calculator. Watch out for your parentheses, because when you push the log button, it opens up a parenthesis that must be closed before you hit the division. And you can see what that is equal to, and it's approximately 2.789. I'll just go to 3 decimal places. If you want to prove that the other part of the change of base formula works as well, why don't you do the same thing, but do natural log of 89 divided by natural log of 5 and see that you get, of course, the same thing. Now, if you have the updated operating system on your TI calculator, you actually can do the change of base formula quite easily. If you go to Math, when you push Math, you can push the up arrow button twice, or you can go all the way down to, I believe it's letter A, and it says log base. It's a little log base thing. What that'll do is it'll call up a log symbol, and it'll give you a little box for your base, and it'll give a little box for the number. So that's very convenient, and you don't really even need the change of base formula if you have this on your calculator. So you can practice that. And why don't you do the log base 5 of 89 and make sure that it says 2.789. So that's the change of base formula. And again, I'll prove that to you a little bit later. Thanks for watching this, and we've got some practice to do in class. See ya.